It's a great pleasure and a great honor to be here. In particular, it's a great honor to give a lecture that is named after Aneesur Rahman, who actually initiated the field of molecular dynamics. Although I had the chance to meet with Anees only very sporadically, I met him, I saw the first time him when he was giving a lecture at IBM where I was as a postdoc in Yorktown Heights. It was a great lecture. and then I met him when he moved to Minneapolis, and he was already not in very good health when he was there. But I remember I've been very close all these years with Michele Parinello, and Michele was really very, very close to Anees. He was always talking about him, and it was deeply saddened when Anees passed abruptly away. So that's what I would say. So in my talk today, I'm going to discuss water in a wide range of regime, from glassy, amorphous, from glassy water to deeply undercooled water, to water at ambient condition, to water in, let me see if this thing works. Yeah, to water at extreme pressure. So water has a very rich phase diagram. This is just, you see all the stable structure of water, but today I'm going to spend time also discussing metastable states of water. And the reason for this very rich structure is that water has a hydrogen bond network. This is a dominant feature up to rather high pressure. And here, this is an example of a hydrogen bond network. You see these water molecules that are bonded by hydrogen bond, and this is an ordered structure. This is ice, an ice structure. You see that there are these ring of bonds, and the shortest path that one can make to come back to the same molecule is a six-fold ring. Instead, here, this is the network in liquid water, how it would look like in a snapshot. And in that case, the distribution of the ring becomes a disordered distribution, and from the distribution of the ring, with different sizes, no longer just six-fold shortest ring, but also five-fold, seven-fold, and so on, one can learn about the network, and the different structure that water has are related to the rearrangement in this hydrogen bond network. On the other hand, when we go to very high pressure, I will discuss at the end of the talk very high pressure, in particular superionic ices. In this, I'm going up to pressure of about 2 terapascals, so rather extreme. And in that case, one has a quite different system in which the hydrogen bond network is lost, and the water molecule do not exist any longer as individual molecule, but one has a system that is made up by ions. Of course, in order to explore this different range of structure, one has to deal with the fact that there are vastly different time scales that are associated to that. Extremely long time scale when we deal with network relaxation, and particularly at very low temperature. And on the other hand, we have fast phenomena in the superionic phases. So it is impossible to deal with all these phases by using a unique approach. One needs to use approaches that require different level of coarse graining to deal with the slowest phenomena, up to ab initio molecular dynamics when the time scale is sufficiently fast. So let me start with glassy water. And this is just a pressure versus temperature phase diagram. You see here we have stable water. This is the melting line. This green area is the area that one can access by supercooling in experiment bulk, neat water, but one cannot go below this line because at this point ice nucleation will take over. On the other hand, if one quench the liquid, one obtains disordered structure that are this structure here indicated below, low density amorphous ice, high density amorphous ice. You see this structure actually exists and can be made in experiments. And here again, if we raise the temperature in this amorphous ice, if we go above a certain temperature, crystallization will occur. And so there is this white area here that has been dubbed the no man's land because it is very difficult to access it from experiment. Now, let me just focus a moment on these two glassy polymorphs. These two glassy polymorphs are separated by a first-order transition, even though they are metastable structure, but there is a first-order phase separation line that separates these two, and in fact, one has a typical van der Waals loop in this PV diagram. If one follows the isotherm by applying pressure and then depressurizing the system. So there is indeed a firmly established first-order separation line between these two amorphous ices. And what happens is that in these two amorphous ices, there are different local environment of the water molecule, and the different local environment of the water molecule are better captured by an order parameter that I indicate here. This local structure index was introduced by this Shiratani and Sasai in '96, and essentially is an order parameter that depends on the coordinate of the molecules that are in the nearest neighbor shell and between and in the shell in the region between the first and the second coordination shell, and is very sensitive, is able to distinguish structure in which these two shells are well defined from structure in which there is more disorder and that occur at high pressure. So this is characterized by a low value of disorder parameter. This is characterized by high value of disorder parameter. One thing that I want to mention here, however, is that both when the system is in this structure, which would be the structure that corresponds to high density amorphous ice, and when the system is in this structure, each water molecule is still tetrahedrally coordinated. So the defects, there are certainly in the real material, there are defects, but coordination defects, but these defects are not important to understand the structure. So the first question that I was asking myself is why LDA and HDA? And so I want to take away the defect, and I use just a very simple model. I'm an old person who worked on silicon semiconductor in the 80s, and there was this model that I call here WWW that was due to Dennis Ware, Fred Wooten, and Weiner, in which they just gave a prescription to generate tetrahedrally coordinated continuous random network with periodic boundary condition. This different network can be explored by Monte Carlo via elementary bond switches, one is indicated here, and relaxation moves guided by an ultra-simplified potential, just the Keating potential in which there are just bond stretching and bond bending. So even with this very simple potential, something that comes out that is quite interesting is that if we now generate these structures, amorphous structures, by quenching the liquid structure of this continuous random network, which will correspond to continuous acceptance of these bond switching moves, We do just a simulated annealing on this thing. What we find is that if we vary the volume of the cell or the density, essentially this local structure index, this local environment index, vary very little. But when the density exceeds a certain value, there is a sharp drop in the local structure index, signaling that one is actually sampling a high density eye structure. And one can see this thing from the distribution of the ring that I mentioned before. One can see that the ring distribution is dominated by six-fold rings in the low density structure, but after, I think that these are different ring distribution obtained at these various points here. They differ very little from one another until when there is this drop, there is a drastic variation also in the ring distribution. One gets a much broader distribution of the ring, increase in entropy, increase in disorder in the structure, and that is due to the fact that essentially the physics is very simple. The physics is that when you apply pressure or you reduce the volume, you introduce a strain in the system. The Keating potential is optimized to be zero, say, in the crystalline structure, and it describes deviation, excitation with respect to this crystalline structure. As the strain that you build in can no longer be accommodated by short member rings centered around six-fold rings that can be done if the volume is, does not change too much, the system can still accommodate then that by just small changes in the bond length and in the bond angles. But when you exceed a certain value, what happens is that the system has to gain in enthalpy by increasing the disorder, and can gain in enthalpy by increasing the disorder by allowing for a larger packing that occur, as I show in this local structure index, by having longer member rings that can deform and can put more interstitial molecules close to the central molecule when we go, we look at this coordination structure, but still in a way that keeps all the molecules perfectly tetrahedrally coordinated. So that is something that is a very simple thing, but I don't think it was known. In fact, from this thing, we use this technique. Now I'm quite interested, in fact, let me go back to this thing, in studying more in detail the statistical mechanics of this system, and in studying what happens if here there is only tetrahedrality that is present. But suppose that we have also hydrogen bond. Hydrogen bond means that the bond do not have just tetrahedral angles, but they have a direction. And there are donors and acceptor bonds. And there is a constraint that there are always two donors and two acceptor bonds for every site in the network. This local constraint introduces longer range correlation in the system, and that probably will modify the statistical mechanics of this model, but that is something that is work going on. So let me just say that one can use this simple model to actually generate true LDA and HDA structures that we can compare with experiment. In the previous one that I showed, this transparency was using just the Keating potential appropriate for silicon. Here we used a potential that is adjusted to ice. And once we generate the network structure, we can then locally refine this structure by doing ab initio molecular dynamics with color noise. That was a technique introduced by Michele and collaborator to include quantum zero-point motion in the system. And this is the structure that we get with this technique compare with experimental neutron diffraction data. And one can see, notice the collapse of the second shell of neighbors in high-density amorphous ice, and one can see the ring distribution in this low-density and high-density amorphous ice, and compare with the ring distribution that we have, one find in simulation for ambient water, which indicates that ambient water indeed has similarity, is more similar to high-density ice, to high-density amorphous than to the low-density amorphous. So this is to say, of course, one can do then other things, study properties of this system, but this is already something that we learn when we consider this network. Let me now move on. I have discussed so far what happens here, why we have, I think that the physics, why we have these two glassy polymorphs is actually quite simple. And it can be understood by considering ideal glassy structure like this continuous random network. Of course, if one wants, with a realistic potential, to generate this thing by doing what is done in experiment, one will have to overcome incredibly large time scale. That is definitely not possible, and one will introduce always defects that more than there are in real experiment. But let me move on. So since one has this first order separation line here, one may think that this first order separation line could continue for a while in this metastable liquid water and eventually terminate at a critical point. That kind of idea was actually put forward by Gene Stanley and collaborators in the early 90s. And so one will have here this low-density liquid and this high-density liquid, and has been put forward based on computer simulation, because experiment cannot access this region. Even though nowadays people are starting to do experiments where they can undercool droplets and using free electron laser, there has been some very nice experiment, but of course then they have the difficulty how they can control the pressure in this system is not that easy. So anyhow, with computer simulation, one can overcome the fate of crystallization, because if one does a sufficiently small system, one will have the system to persist for a while before crystallization takes over, and one can study this thing. Now, the presence of this second critical point, this is an hypothesis, would provide an elegant explanation of the water anomalies. There are, as you all know, water has a lot of anomalies, and in these anomalies there is the fact that response function of the liquid show a kind of divergent behavior, at least an incipient divergent behavior, as one reduces the temperature. So the fluctuation in this system increase systematically by reducing the temperature. Of course, the fact that this fluctuation increase systematically by reducing the temperature can also be accounted for by models that do not imply criticality, but I think that this hypothesis provides an elegant explanation for this fact. So, as the no man's land is impervious to experiment, we use computer simulation to access it. And as in several places in my talk, the Aneesur legacy is present, we use now a different level of coarse graining. In this case, we have a real molecule, or say molecule, no longer just a continuous random network, as in the model that I described before, And we use here this, what is called the StTo model for water that was introduced in the 70s by Frank Stillinger and Aneesur Rahman. In this model, one has, each molecule is just a sort of little tetrahedron, is a rigid little tetrahedron with charges associated to these different spheres, and the parameters are adjusted so to reproduce the properties of water. Now, the key question that we ask, of course, many people have done that, and key question that we asked ourselves when we started this work was, is the transition genuinely first order? Why is the local density liquid metastable? Because it was suggested that the local density liquid would vanish if the crystal phase is also sampled. And again, using this different, this different approach, we use several Monte Carlo technique and sampling technique. Here I just mentioned umbrella sampling, but we use also other technique like well-tempered metadynamics and replica exchange and so on. And the result that we get, this is the free energy surface that is described in terms of two order parameters. One is the density and the other is the Q6 order parameter. The Q6 was introduced by Paul Steinhardt, again, many years ago. And is able to describe, this we use here a global Q6, so the global Q6 is able to describe, to distinguish well between structures that are crystalline from structures that are amorphous. In fact, in the infinite size limit, the Q6 for this amorphous structure should be 0. It is different from 0 because we have a finite sample, and here we have the crystal, and here we have, so this is the free energy surface, and we see that there are two basins that correspond to this high density and low density liquids, and these are snapshots of the corresponding structures, and one can see here, if one drives the transition from this low density liquid to the crystal that one gets here is cubic ice rather than hexagonal ice, but it may be that even in experiment when the system is deeply undercooled, that nucleation may be dominated by the, initially, at least in the initial state, by the cubic ice. So that is what one sees here. Now, in order to study this thing in more detail, what we did was to do some limited finite size scaling, and we could do that for a certain range of sizes, not too large, because of computational limits. But here we plot, as a function of the number of molecules in the simulation cell, we plot the barrier, the free energy barrier at coexistence. If we have a first order separation line, this should increase like the surface separating the two coexisting liquids, and indeed the simulation data are consistent with this result. And if we look also at the Q6 order parameter, we see that the Q6 order parameter goes to 0, the average Q6 goes to 0 as we increase the size of the system as 1 over the square root of n, as it should. And this is just a snapshot of the simulation in which we have colored differently. This is the simulation box that has been repeated, and these are molecules that correspond to the high density and low density structure that are characterized by different local structure index parameters. So this is what comes in there. So the thing that I want to just say, I want just to make one comment here, and the comment that I want to make is that if we look at this free energy surface that now is represented here, not just projected on a plane, we see that the depth of these two basins, now this is a coexistence between these two liquids, and this is the ice phase. The barrier that separates the two liquids is of the same order as the barrier that separates this liquid from ice. So that we learn an important thing in doing that, is that the fact that we can sample this low density liquid has to do with the kinetics. The kinetics of ice nucleation is significantly slower than the relaxation processes in the liquid, and so kinetics has an important role. In fact, we knew that already, because if one does not use this model, this StTo model, but for instance, one uses what is called in the water community is called the MW potential model, the Moore-Molinaro water potential. The Moore-Molinaro water potential is just a Stillinger-Weber potential. So that the potential that includes tetrahydrality, Stillinger-Weber was introduced for describing silicon. As I said, having a long experience with that, I know this thing quite well. In this model, there is tetrahydrality, but there are no hydrogen bonds. Instead, in this StTo, there are charges and there are hydrogen bonds. So the kinetics, due to the presence of the hydrogen bonds, is much slower, and that is what can make this thing to happen. Because if one does the simulation with the Molinaro potential, one inevitably does not get a stable low-density liquid, but one gets very rapid crystallization. So this brings me back to the issue that I raised at the very beginning, that is something quite interesting to study now, is to study whether we can understand this effect in the context of this coarse-grained model that I mentioned at the very beginning. Because there we could introduce hydrogen bond just by associating arrows to the link between two sites, and that does not need to do expensive calculation of the electrostatic energy with Ewald summation and this kind of thing, and one can study in detail what this thing gives rise to. So that's, I can now conclude more or less this part of the talk by making a few comments. Only experiment can falsify this scenario. However, using advanced computational technique, we have demonstrated that water-like model can exhibit liquid-liquid immiscibility. The coexisting liquids are metastable with respect to ice. A first-order phase transition occurs between the liquid. Kinetics is important. Open question, what determines the separation of time scale? Is StTo relevant for real water? And here is just indicated these donor and acceptor hydrogen bonds. Now, before moving to the next part of the talk, I want just to show this very nice movie that I just took from this work by Yagasaki, Matsumoto, and Tanaka. Is in the supplementary material of their paper. They did a molecular dynamic simulation of this StTo model rather than studying the free energy surface as we did with this advanced sampling method. And they did that in a parallelepiped cell, so that the surface separating, if there is a spontaneous phase separation, that will occur along the surface that is orthogonal to the long direction. And that is indeed what is going to happen. So they start with a a liquid that has been quenched to a simulation to the thermodynamic condition of coexistence between the two metastable liquid. And what one sees here, let me see if I'm able to do that. So over a very short time scale of about 10, 20 nanoseconds, there is a separation between these two liquids. And this is the low density liquid. The surface, the interface is fluctuating, and there are, once in a while, little ice nuclei that form but disappear. And eventually, let's see, this thing goes on. So you see here, this is 400 nanoseconds. Eventually, at some point, some bigger nuclei will start to form, and after 600 or 700 nanoseconds, you see that ice start forming, and what you see here now, there is ice, and eventually you get all this ice over here. And of course, since this is a fixed volume, there is also a high density liquid that has to remain there. And that is, I think, a nice movie that is quite consistent with the free energy result that we shown before. Now, I want to move on and discuss ambient water using ab initio molecular dynamics. Now, ambient water is a very challenging system because it has all these strange properties, this separation of time scales, as I already mentioned. But to do water with ab initio molecular dynamics is also particularly challenging. It's particularly challenging because these water molecules interact weakly among themselves with this hydrogen bond, and there is a balance between hydrogen bonds and also van der Waals or dispersion interaction between the molecules. So what, when we started with Michele many years ago to study liquid water after we developed the Carr-Parinello method, we thought, okay, water is a nice system to do, but it was very hard. It was very hard because if one does at that time, we were doing local density approximation of DFT. With the local density approximation of DFT, the water is a disaster. Luckily, there were these GGA or gradient corrected functional, and with those things improved quite a lot, but not sufficiently. So in order to do a good job for water, what one has to do, one has to use a functional, here we use this PBE0, that is a hybrid functional that includes a fraction of exact exchange, and also we use a self-consistent van der Waals correction that was introduced by Tachenko and Scheffler. With this functional, we get, you see, with PBE, the pair correlation function is much overstructured, and as we move across all these functions, and eventually we get to this one, we get something that compares quite well with experiments. Now here, this is the temperature that has been increased by 30 K. That is because these are classical simulation, and we are now running on this computer here, on this Mira, path integral simulations, but with classical simulation from previous work, we found that an increase of temperature of about 30 K was a reasonable thing to describe the quantum effect on the oxygen pair correlation function. Now, this is a comparison with experiment. You see, this is the structure factor, and this is the correlation function, pair correlation function. The comparison is quite good. I want just to spend a word here to say why there is this difference between these functions. The difference between this functional is better understood if we look here. These are the distribution of what are called the maximally localized Wannier functions. So there are 8 electrons, valence electron per molecule. There are 4 maximally localized Vanier function associated with its molecule. The maximally localized Vanier function is just a unitary transformation in the occupied subspace, and the center of this Vanier function is located here in this bond pair, and here is associated with the lone pair. What one sees is that if one uses functional like PBE, the distance of this center of the Vanier function in water, these are the average distribution from this thing, is larger than if one uses the better functional. And that reflects the fact that the water is much more polarizable if one has this GGA functional, and this gives rise to a stronger hydrogen bond and therefore to an overstructured water. Let me move on. Another thing that we use in this simulation are these van der Waals interaction. These van der Waals interaction are very important because without this van der Waals interaction, the fact that water is actually denser than ice will be reversed, and it would be a disaster if indeed for life, if something like that happened. This is the result, the density discontinuity between the solid and the liquid from experiment. If one does a PBE calculation, one sees that one has the opposite effect. By the way, these simulations are done with constant pressure simulation, and for ice, we actually use the Parinello-Raman for the ice form to do the simulation. So again, a legacy of Aneesur. And one can see that the addition of van der Waals allow to densify the structure, and with the best functional that we have, we get something that is not bad compared to experiment. One can also see here, this is our recent data on the compressibility of liquid water, and one can see that the compressibility from experiment has this value. When we do the best functional, we get this value here, and with PBE and PBE plus van der Waals, even though the PBE plus van der Waals gives a decent discontinuity, at least the right sign, the compressibility is still much lower than what one has in experiment. The reason has to do with the fact that even though the van der Waals allow to densify the structure, they do not change much the structure of the network, as one can see from the bond, from the ring distribution, and one see that indeed one has this broader ring distribution when one uses this other functional that allows for hydrogen bond to break more easily and makes the water more diffusive. So let me just say, well, I want to say a few words on that. The effect of this different functional is extremely more important, is much more, even more important if we start to look. Oh yes, I have to be careful. Thank you. Is actually even more important for defect, and the most important defect, of course, are these intrinsic defect complexes, the hydronium, the hydroxide, and the water radical. The hydronium and the hydroxide are stable defects, so one is positively and the other is negatively charged. So this is neutral, and so again, going back to my old days as a semiconductor guy, this kind of complex is an example of what in the semiconductor physics community was called an Anderson negative U system. And here are the different local structure for the OH radical that one obtained using a functional, our best functional, or using a gradient corrected functional. And one can see the difference is very large in the pair correlation function. This O star is the oxygen of this OH radical, and this again the oxygen of the OH radical, and this is the hydrogen, this guy, of the OH radical. So essentially what one sees from this pair correlation function is that if one uses a GGA functional, this system is give rise to a much more stable defect complex with several bonds between this radical and neighboring molecules. These bonds instead disappear, and only one remain, made by this hydrogen with this with the water molecule here, and other than that, the system does not make any well-defined bond. Is quite hydrophobic. That comes out naturally if we do this functional. And also the other thing that comes out is that both hydronium and hydroxide are stabilized compared to their GGA counterpart, in the sense that proton transfer processes do not occur as often. And the nice thing is that the OH minus is stabilized more than the hydronium, so that what happens is that actually the proton transfer processes are the diffusivity, let's say, of the hydronium, which with GGA will be similar to that of the hydroxide, becomes actually larger than that of the hydroxide, again in agreement with the experiment. I want just to conclude. What happens is that the band structure of the OH radical is quite important. It's a fleeting defect, but it's quite important as to promote oxidation reaction. So that is the kind of thing that we would like to study. And one can see here the band structure, the density of state, a schematic plot of the density of state when we do this calculation for the radical. This is done in a spin polarized calculation. And one can see that if one uses the GGA, of course, one has a smaller gap for this system, but the system is actually metallic, because there is this empty states that is here essentially at the top of the valence band. Instead, when one does the calculation with this other functional, this empty state is pushed up in the gap, and of course these are cone-sham energy, so they are not really removal energy, but we are now doing calculation with both GW techniques and also with other approaches to try to see what would be the ionization level associated with this thing, and we think would be somewhere here in the mid gap, and that should be also consistent with recent experimental observation. Just as I mentioned here, this Anderson negative view, if the system then captures, there is an electron that can be captured by this system, there is a significant rearrangement of the molecule around as the OH minus defect form, and this rearrangement push the level down here at the top of the valence band. This is taken from a work by my former postdoc, Shifan Wu, who is now an assistant professor at Temple, in which one gets the good ionization potential for these states associated with this OH minus defect. So with that, I conclude this part of the talk, and now I'm going to move to switch gear and move to a extremely high pressure water, which, as I said, is made of ions, and the hydrogen bond network is lost. Now, it is important that we can study this system with such important change in the electronic structure, because there is this ab initio molecular dynamics technique that allows to do that. With potentials, we will have to introduce completely different potential to describe this system. And in fact, the the fact that at sufficiently high temperature, the system becomes superionic, meaning that the oxygen sublattice remain crystalline, but the proton sublattice melts, and the proton can diffuse in the structure. And this, in fact, was found in earlier work when was started from this, in which the oxygen is in this BCC phase, this is pressure, was found in a work done in Trieste by was a thesis of a PhD thesis that was directed by Michele and Erio Tosatti in Trieste. And this raised quite some interest because the fact that the system remains electronically insulating, but it is ionically conducting. If one happened to be at this extreme condition that can be found in the mantle of massive planets that are in which there is ice, that can give rise to current that can generate magnetic field that are observed for these planets. So what we did here was to continue this kind of studies using the Parinello-Rahman technique, and we consider now it at very low temperature, stable crystalline phases have been found by several groups using different electronic structure methods. One has this called ICE-10, and then one has this sequence of structures. So we were interested to see if this thing can change also in there are phase transition also in the superionic phases. A transition from BCC to closed packed phase, like hexagonal closed packed or FCC, was also found recently by people in Berkeley who use free energy methods. And we don't use free energy method, but we allow the cell of the system to change with the Parinello-Rahman method. And so we have been able to find that there is a sequence of structure. We go from BCC to closed packing. I call here closed packing because we are not able to distinguish between HCP and FCC. They have very similar energy in the system. We can get one or the other. But in correspondence with that, there is a reduction of the sublattice melting temperature. These two dashed line here represent the melting temperature that we get if we go reversibly up and down in temperature in this system. And what happens is that if we go to even higher pressure between above 1.5 terapascal, there is a new phase that has a sublattice structure that has quite similar to the sublattice structure that one finds in this thing here. And this phase is favored by the fact that this is a binary system, and it allows for more packing when we include both the oxygen and the hydrogen. If we had just the oxygen, of course, one cannot pack more than FCC. But because there are also the hydrogen, this allows for more packing. However, there is a reduction with this larger packing. There is also a reduction in the diffusion constant in the system. It's still diffusive, but less diffusive, so that if we raise the temperature, what we found was that there is the system at the same pressure can also go back to this closed packing structure because they are favored entropically, whereas these structure here are favored enthalpically. So this is what one, let me just be quick on that. The distribution of the Vanier center is quite different from the distribution of the Vanier center that one has in water that I showed before. One does not have any longer this bimodal distribution, but one has a unimodal distribution, which is again consistent with the fact that the system has become a system dominated by ionic effect. And what we have done at this point was to study the character of the superionic transition, similar to work that Giulia did several years ago. And we have actually calculated the conductivity using the Nernst-Einstein relationship that connects that to the diffusivity. And these Z star are the effective charges that are associated with the ions. They are not just the nominal charges associated to the ions because the system still has electrons. The correction coming from the electron is not large though, and one can see that there is a quite different behavior in the way the conductivity goes across the transition in the case of the this structure, this higher pressure structure, this P21C, and this FCC, in which there is a jump. This is in the superionic literature. The presence of a jump is what is called the type 1 superionic system, and this continuous transition is associated to what is called the type 2 superionic system. This behavior correlates extremely well with the behavior that we observe in the oxygen sublattice. Namely, in the oxygen sublattice, when the system goes to the FCC structure, the oxygen sublattice at low temperature has a different structure because the proton occupied certain site and there is a change of symmetry in the system. And if we monitor the mean square displacement when the system is at low temperature across the phase transition, the superionic phase transition, one sees that there is a sudden jump, small, but this is the mean square displacement, a jump in the mean square displacement in the case of this FCC structure, but there is no jump, there is rather a continuous evolution when we look at this other system. And these are typical conductivity data taken from an old review paper. One shows that these are typical superionic material. This is the one that exhibits the jump. This is the one in which the conductivity changes continuously. And this is a third type that is less interesting, in which the conductivity shows Arrhenius behavior. So with that, let me just, this is a very last thing. So these are trajectories in this superionic system. You see that the oxygen remain at their sites, but the hydrogen or the proton can actually move around, and they are connected all over the system. Now, this this plot is a comparison with the phonon density of states as calculated by Andreas Hermann, Neil Ashcroft, and Roald Hoffman in P21C at low temperature, so when it is a crystalline form, and these refer to the system with hydrogen, these refer with the system with deuterons. And the red line refers to the oxygen density of state, this green one refers to the proton density of state. The black lines are the density of state that we get from the power spectrum of the velocity autocorrelation function in the system. So you see that there is a close similarity, but there are diffusive modes that are present in the case of the superionic system compared to the system at low temperature. Now, why do I show that? Because because of this very large pressure, there are modes at extremely high frequency, and the zero-point motion effect is quite large in this system. So that raises an interesting question that is, however, quite challenging. Would it be possible to have some sort of quantum melting in this system rather than just a classical melting? That is something that we would like to investigate, but it's quite difficult. So with that, I think I can come to the conclusion. As we have seen, water is a fascinating system, a different thermodynamic condition. There are very different states of matter that occur with wide changes in the nature of bonding, molecular versus ionic phase, and relaxation processes, network relaxation versus local atomistic. Computer simulation from coarse grain model to force field model and ab initio simulation constitute a valuable complement to experiment and even a substitute to experiment at conditions that are not currently accessible by experimental means. And with that, I would like to thank you for your attention. And I have here, well, this is several people have collaborated in this research, and I have to acknowledge funding from the DOE, some of which is now running out. And I have also to acknowledge computing facilities and in particular the Mira machine here at A&M. Thank you very much.
Thank you. Maybe there's time just for one or two quick questions, if there are.
Did you answer the question about whether StTo water has any bearing on real water?
No.
then could you answer two questions?
Yes.
And the first one is, why did you guys pick StTo water? And then the second is, have you thought about doing this calculation again with something like Francesco's new model or something that we think is very accurate?
Yes. The reason why we picked StTo is that StTo gives an overstructured water. And it has, StTo water has a freezing temperature that is around 300 Kelvin. And for ice, hexagonal ice, and it's 270, around 274 cubic ice. The fact that it's slightly overstructured helps because it allows to find this phase separation at temperature that are not too low. They are low, but not too low. To do with better model potentials, like for instance tip 4P or Francesco's. Well, Francesco's is very nice. I'm not sure how does it compare in terms of cost with tip 4P, because I think it's probably more expensive.
It's a lot more. Yeah.
So we will be already quite happy if we were able to do it with tip 4P. However, with tip 4P, one has to go to lower temperature and relaxation processes are very slow. We have made some attempt, but so far we have not been able to get a definite answer. Certainly, well, just to say one thing to Greg, having a very effective sampling method would help.
Roberto, do you think there could be an electronic signature of low density and high density ice?
Oh, sure. There are electronic signatures because I didn't present that, but for instance, if one does this X-ray absorption spectra, there are also probably other signatures, but the one that we did indeed calculate is this with this model that I discussed. Basically, there are these X-ray absorption spectra. In this X-ray absorption spectra, that was a very nice experiment that John Tse and collaborator did several years ago, well, 2008 or so. What they saw is that this X-ray absorption spectra has three dominant features. Forget about the pre-edge, what is called the pre-edge in the spectrum. But if one considers the main edge of the spectrum, there are these two features, and the weight of these two features is reversed if you go from low density amorphous to high density amorphous. The same thing occurs also if you look at ice and liquid water at ambient conditions. So there is precisely this kind of thing, and this kind of thing, in my opinion, and according to the calculation that we have done, is precisely related to the fact that the network structure has changed when we go from low density to high density.
I'm going to ask one quick question. Is there such a situation that occurs for silicon? Is there a high density and low density amorphous
Well,
phase of silicon? So almost the implication is they used a Keating model to get there.
yeah, the difference, I think, is that in silicon, it's a small gap semiconductor, and when you get the metallic silicon is conducting. So if you get, you can get, if you quench instantaneously the liquid, you may get some metallic system.
But actually, you'd already have metallic system.
Yeah,
That's
exactly.
sort of why you do this.
Exactly.
And sort of lastly, is anybody looking for a protonic superfluid then? I mean, if you have
that is what that is the thing that we would like to look at.
Right. Have some sense about what conditions, some planet somewhere that we can find?
Well, that, I mean, even if I don't know in which planet that could happen, if that were going to happen, would be extremely interesting, because if one can have that kind of thing, that would be a realization of a super solid.
Right.
And, well...
very interesting indeed. So,
yeah.
So one last thing.
Wow. Oh, thank you very much.
Thank you again, actually, for a wonderful
Thank you.
lecture.
Thank you.